Hello everyone. Today is day 13 of our challenge doing 30 deep learning projects in 30 days. So coming to the list of our problems, the problem 13 is to explore image segmentation with UNet for a small portion of Carvana dataset. If I look at the Carvana image masking dataset, the dataset looks like this. Okay, so I guess this is again, I'm really happy. So I really find computer vision related problems a little fun. So yeah, this is again one from computer vision. So yes, let's start. The flow is going to be same. We will go and take the help from ChatGPT, ask questions to give me the code and everything. So let's start. I'm going to use the same window as I have used for all our previous problems. So I'll say, hey, it is day 13 and here is the problem. Okay, let's wait for it to generate everything and then we will look at the code. Okay, so a lot of looking at the just a second. Huh? Looking at the steps, I see we might be using a lot of things uh, today. Yes, we may be looking at the code. A lot of things we'll be using today. It is going to be a combination of TensorFlow and OpenCV. So good. Yeah, and yes, then we'll be loading the images and building the unit model. A good thing, and then compile the model, evaluate the performance of the model, which is also a good thing. So yeah, this is something really good, good, also not as mundane or a little complex than all our previous problems. So yes, so it says you might be hearing a little from the background. It is my washing machine. I'm really sorry for it, but yeah, I'll try to come closer to the microphone so that my voice becomes clear. So yes, it says that um, Day 13 brings a deep dive into image segmentation with UNet, a powerful neural network architecture for segmentation tasks. The Carvana dataset is perfect for this as it involves segmentation for car images. Okay, Carvana dataset involves segmentation of car images, which makes the task visually interesting and a great learning experience. Okay, so what are we going to do? Deep dive into image segmentation. So this is a new thing today you with UNet, a powerful neural network architecture for segmentation tasks. Okay, so we will explore this UNet neural network architecture. Then for dataset, this dataset we are going to use, which involves segmentation of car images. Okay, great. So the overview of image segmentation and UNet is that image segmentation is the process of labeling every pixel in an image such that parts of the image are identified. Different parts of the image are identified. Okay. For instance, you might want to segment cars from background so that each pixel belongs to either the car or the background. Okay. So we So it is the process of labeling every pixel in an image such that different parts of the image are identified. For example, let's say I have this image. Maybe I can label each pixel as whether it is part of the background or whether it is part of the car. So if this pixel belongs to the car, I'll say pixel. I'll label that pixel as car. If that pixel is lying here, I'll label it as background. So this is how this is what it is going to look like. Not here, yes. UNet is a powerful convolutional neural network used for image segmentation. Okay, it is named UNet. due to its U-shaped architecture. So it is named U-net because of its shape, U-shaped architecture. Okay, this is like an encoder where features are extracted from. So it consists of two things: contracting path and expanding path. Contracting path is like an encoder which extracts the which where features are extracted and the image resolution decreases. Okay, and expanding path is like decoder where the special resolution is gradually restored to produce the segmentation map. Okay, let's I would still go a little deeper to understand these two things. I have not understood, but let's go and let me see before. I mean, what is all there before we actually start coding, and then I'll ask. The Carvana dataset is a dataset of car images that come with corresponding masks indicating which part of the image contains the car, allowing you to train the model to segment cars from there. Okay, Carvana dataset is the collection of cars where each contain corresponding mask indicating which part of the image contains the car. Okay, and that is why we can use it for segmentation. Okay, steps for today's project is to set up environment, import required libraries. Okay, we will load and visualize the dataset. Okay, pre-process the data for unit. That is, I mean, I don't know, maybe we need to resize the images and normalize the images. Okay, we have been doing it, so it is not something new. Then we will build the unit model, and then we will compile and train the model. Okay, evaluate the model and visualize segmentation. This is something new by the name if we go. So this is something new. So yeah, before starting, I'll say I did not understand much about the UNet uh, two subpoints: contracting path and expanding path. Can you please, not Elise, please explain with easy examples? So let's wait for it to generate everything. Okay, it has generated everything. Let's come start and understanding what unit convolution model is and how does it work. So unit is a convolutional neural network, okay, used for image segmentation. Okay, where the goal is to label every pixel in an image. The network, where the goal is to label every pixel in the image. The network is called unit because its architecture looks like a U shape, where the input moves through an encoder and then through decoder. So it moves from encoder and then decoder. That's why the shape is U. We will look at the shape, and what we have understood is that it is used for image segmentation, where the goal is that is to label every pixel of the image. Think of it like photo editing tool. Okay, that helps identifying different parts of an image, like separating the car from the background. Okay, like separating cars from the background. The unit model helps it take an input image, transform it into a new version of the image where each pixel is assigned a label indicating whether it belongs to a particular object, car or background. Yes, we have talked about it. Something like this, where each label belongs to what? A car or the background. Like this. The two main parts of unit are encoder and decoder. Encoder is called as contracting path. Decoder is called as decoder path, expanding path. The encoder, the contracting path is the left side of the U. Okay, this one. It is designed to extract features from the input while reducing the special dimensions. Think of it like zooming out and summarizing what image contains. Okay. The how it works. The encoder takes the input image, passes it through several convolution layers. At each step, the resolution of the image gets smaller, but we learn more. But we learn more features. Okay. The network learns what is present in the image by focusing on different features like edges, textures, and shape. Okay. This process is also called downsampling. Hmm. In Yes, and imagine you have a high resolution picture of a city street and want to understand what is in it. You could do the following. You zoom out so that the details like individual windows or road signs become less visible, but you can easily see the main component like building, cars, and roads. You zoom out so that the details in like individual windows, road signs become less visible, but you can easily see the main components like building, car, and roads. Okay. Imagine we have a high resolution picture of a city street and want to understand what is in it. You can do the following. Okay. In each step of zooming out, you summarize what is in the image. You start with tiny details. Okay. Okay, so we are zooming out. When we zoom out, we will see the individual windows of the building and the road signs. They become less visible because we are zooming out of the image. But let me use chat GPT only to generate an image like this. Can you generate an image of a city street with buildings and trees? Okay, so if I see this image and open image in a new tab and then open image here, let's say I have zoomed in. Now if you see, I can see this thing clearly. Now if I zoom out, I would be able to see the edges of the building, the cars, and everything, right? So this is what it is saying. When we zoom out, we see the main components like building, cars, and roads. In each step of zooming out, you summarize what is in the image. You start with tiny details like windows, then move out to larger concepts. That is zooming out. That is contracting path. In UNet, you pass the image through convolutional layers that learn important features you and use max pooling layers to reduce the special resolution. For example, an input image of size 128 by 128 pixel becomes 64 by 64 after first downsampling, and then 32 by 32 pixel, and so on. So we have a zoomed out picture. Then we s- keep smalling it. We will keep lowering the size so that we zoom out so that we see the overall content of the image, like what is in the image: a building, a car, road, a flyover, or what is. Yes, exactly. So what is present in the image. So This is what contracting path looks like. Okay, this is what contracting path look like. Okay, a decoder, the expanding path is the right side of the u. This is this expanding path. It is designed to reconstruct the image by gradually increasing its resolution. So it reconstruct the image by gradually increasing its resolution. So it goes back to where it started from in the encoder path. The goal is to recover special details while making pixel-wise prediction, deciding whether each pixel belong to an object or not. Now we know what objects are there. So in the first step, I what I think is first step is used to predict. First step is used to find out how what objects are there in the image, and then second is to figure out if that pixel belongs to that image object or not. So a pixel wise prediction is used deciding whether each pixel belongs to an object or not. How it works: the decoder takes the features learned by an encoder and unsamples them back to the original resolution. The process involves unsampling to gradually increase the special dimensions. During this process, the network reuses features from the contracting path through corrections. This helps in accurately identifying smaller details and ensures the segmentation is precise. Okay, I understood that. When we zoom in step by step, adding more details in each step. For example, we have a detailed sketch of a scene. So in the same example of city street, now that you know the general features of the street are, imagine you are trying to create a detailed sketch of the scene. You zoom in uh, step by step, adding more details in each step. Yes, exactly. And remember the features you had noticed before, and use it's this knowledge to create the scene. So from the encoding path, we knew how many features are there. Now we are zooming it and figuring out how each feature looks like, how each object looks like. So this is how the encoding path looks like. We will understand it later when we'll be coding. Yeah, so the encoding and decoding path, now they make sense to me. So I'll now move and start coding from the step number one. It says that we need to have TensorFlow, OpenCV, and Matplot library. We have all of that already installed. I'm a little curious which. Yeah, exactly, I'm using the same correct context window. So yes, I have it all, so I am not going to install it. So I'll go here and create a new file for today's problem. It is going to be day 13.py. Add it to the git repository, mention what the problem is about. Problem is this. Okay, this. um, and just a second. And let's start. The step is import TensorFlow as TF, import matplot library.py plot as PLT. Then let me see how many layers we want to import. We have to import convolutional 2D, max pooling 2D. We have understood all about these layers in detail in the past problem, so I would recommend to go and check out them. And then upsampling 2D. Okay, this is something new. Concatenate new and input. So from TensorFlow dot keras dot layers import convolution to the max polling to the 2D input upsampling 2D concatenate and input. Then we have to import the model from TensorFlow keras, not TSL, keras models, import model from numpy cv2 and os. Import numpy as np, import cv2 in, not in cv2, import os. Yes, we have already imported, and then let's load and visualize the data. So we need to download the data from here. Let's download the dataset from here. Where can we download the dataset from? So the dataset is like, it contains the training image, test image. Uh-huh. Let's download all. Why do you have to do this? Okay, let me. I Let me do what? Let me stop the recording and download it. So I have accepted the rules. I have to now just download the data. I'll go and download it. Why I did that? Because I wanted not to show my phone number. And I am a lazy person. I don't want to go and edit with asterisk this part of the video. So like, okay, let me pause the video. It is downloading. Let me see. Okay, this is of 24.4 GB. Oh my god. Let me see what is there, what is needed here. Images and masks. Image directory, test, train, train mask. I mean, they're training set images. Okay. This folder contains, let me see, Kaggle. It says I can download it from here. Let me ask ChatGPT only. Sort not code. I want to see. I'll say the data set from Kaggle contains these files. Which one to load? Okay, for this we are interested in training unit model for image segment. Therefore, we need both training images and there is corresponding segmentation mask. Relevant finds, this folder contains the training set images. These are input images that you will use to train your unit model. And train mask, this folder contains the training segmentation framework. So in the GIF format, for training images in the GIF format. Okay, these masks label which parts of the image belong to the car. Okay, it marks label that which part of the image belongs to the car. So we need to load train and train masks. So I'll stop it. It is going to take a lot of time. So I'm going to need train and train mask. Which file I need? Let me come here. So I may be needing train mask. Train. This I will need. And train mask. This I will need. I don't want in high quality. I'm okay with the low quality. So yes, they both the files will be downloaded pretty quickly. So I'll go here to the downloads folder. I can see the. Let's wait for it to be downloaded completely. It might not take longer. Almost done. Okay. So I'll unzip it, unzip it, and let's check out. Okay. Okay. So these are the car images. Let's unzip this also. This is the mask images. Okay, we can see that they look like this. Yes, pretty cool, right? So I'm going to move them to what our data set. Then data set. Let's move them to our data set. So I'm going to do what? Move download. I'll create a new data, folder here. Set, and here it is going to be Carvana. Not this one. This is the old image. Carvana. Too much confusion. Carvana. So I've created a new directory here inside the dataset folder called Carvana. I'm going to move the uh, directory. Which one? Train, train to our dataset Carvana. Uh, okay, I do not have to mention the directory this option. Now I will move the train mask now. Move to the Carvana again. Now we should have two folders inside our Carvana dataset Carvana directory. So we are now done with the dataset, downloading the dataset of for our problem today. So let's start with mentioning the path for it. So it is going to be set the path to the data set, the path to the data set. So it is going to be image directory. Image directory is path, oh, data set Carvana train. And why am I commenting it? Okay. Then we have the mask directory. Mask directory is copy paste, and this is train masks. Done. Now load the sample image and mask to visualize. Load the sample image and mask to visualize. Okay. Does it has anything like that? No, it does not have the card. And so I don't have the car underscore one naming convention. Instead, I have some unique IDs. So let's do what? Let's load an image. Image is going to be CV2. I am read, I guess. Yes. OS part dot join. Okay. From this OS package path join image directory, and the name is, let's copy this name, copy, paste. Okay, then we load the masked image. I am read OS path join, not image, mask directory, and the same thing, not this. Let's copy it, copy, and this is the name. Let me do one more thing here. Let's give some space so that we can see everything here, not at the bottom, the code that I'm doing coding at the top. And the masked image should be in the grayscale, so mention that also. CV2 gray image. I am read grayscale. I am read grayscale. Okay. Once done, what are we going to do? Resize both image masked with same size. Okay, we are resizing to 128. Resize both image and mask to same size, which is 128 by 128 pixel. So image is going to be image reshape, I guess, right? Not reshape. CV2 resize. Mention the image and the size 128. Do the same with the mask. Resize mask 128. Now we have to do normalize the pixel values in so image is not import, image will be 255.4, mask will be we have been normalizing all our values in all our previous problems, so we know why we do that. Now plot the image and its corresponding mask. Okay, nice. This is something nice. Now we'll run this script before moving to the next step. Visualize the plot the image and its corresponding mask. Plot the image and its corresponding mask. Okay, how do we do that? Plot figure subplot, we mentioned 1 to 1. uh, uh, First image we are going to have car image, where the image will look like this. Second plot will be of this. And okay, let's do that. Figure fixed size. What is the fixed size it is taking? 10:5. We are going to plot subplot. There are going to be two subplot of size 1:2, and this is the first subplot. If I here number of rows, number of columns, and index. So one row, two columns, and first subplot. The title is car image. Then I show the image using IM show. CV2 convert to color the image and mention the image BGR to RBG. Okay. CV2 to I am show CV2 to convert to color this image and convert to CV2 to RG color BGR. If you remember, we did something like this: color BGR to RGB BGR. So ideally, in the in the I guess yesterday we did something a VGG16 model, right? It accepts the image in the BGR format. So we are converting it into RGB format, and then we do what? Plot the second subplot, one row, two column, and this is the second subplot, one to two. The title is mask. Then we'll I'm show I am convert to color. Are we converting it to color? No, we're just showing it. So this is this mask CMAP gray, and then show. Done. Let's do what? Let's run this. Clear the terminal. Clear it. Run day 13.py, and we have an error. So the error is at line number 16. So it says, okay, mask directory. Okay, uh, in my case, the mask is in the GIF format, and this is throwing error. This is throwing error. Hmm. So we're creating a function, load the image. Okay. So this will convert them into mask. So we need to convert them into NumPy. Hmm. Hmm. So it says GIF files are different from other formats like JPG. If we would have had it in JPG, it was easier. Otherwise, now we have to convert it. I don't want to go deep into conversion because then I'll deviate from the main topic to understand the segmentation today. So I'm finding ways to get away with it. Um, I'm just saying, I'm just looking at the code I just want to look at the code and see, are we actually going to use the images, all the images? If not, then I'll just go and convert this image into JPG. It says let's prepare a small training data set. We'll create a Python function to load a batch of images and mask. So load images and mask. Okay, here we mention the, okay. So it does convert it into GIF. So why do I even need to do that? So the image, see, I am read. Okay, it is converting them and then doing it. I don't think we need it, like, right? And what are we doing here? What does it say? Okay, I see we are converting the image, mask images from JPG to mask.gif, and I already have it with me. Don't you think I have an advantage? In step 3, I can manually convert the GIF, one GIF image to JPG for step 2, and and can you update the rest of the steps to for GIF? Yes, see, we already have the mask image in GIF format. We can directly work with them without having to convert eGIF into another format. To make it simpler, I'll update the rest of the code to work with the GIF mask files directly. Since we already handle GIF format and data loading functions, we can skip the manual conversion and work straight from providing dataset. Okay. Loading and pre-process. So it skips the part 2 that we are doing. Loading and pre-processing, training images and masks, building unit model, then compile the model. And okay, so let's split this video into two parts. I don't want to overwhelm myself and I don't want to overwhelm anyone else. We have understood what a unit is, all about the images and everything. We have also looked into the steps and saw that we already have the image in the GIF format, so we do not have to convert them. Um, um, so I'll ask just a thing. Why is it needed if I already have images in GIF? Exactly, it is generating the corresponding mask file names, so I do not have to convert, explicitly convert them. That each image and its mask have similar file names but extensions. I'm a little confused. I need more time to understand this. It says I can say this is can so this is the file name, and for image and mask. Exactly. So the file name we have is this, and the mask file name is like is in this way. So the corrected approach would be, in order to properly construct the mask path, we need to make sure that the file mask file name matches the corresponding image file name with underscore mask added before the extension. This means that for every image file name, we need to append underscore mask before changing the extension to GIF. So for an image named this, the corresponding mask name will be the mask corresponding mask will be named as the file name underscore mask dot gif. Okay, okay. So we are creating the name of the mask. Okay, I got confused. Okay. Let me read the code a little bit. So we are loading the images. Then we skip the hidden files if any. Okay. Construct the parts for to image and corresponding mask. Okay, so you get the image path. Then we get the image base name, mask name, and mask path. Load the image from OpenCV. Okay, we load the images and resize them to normalize them. And then what we do, we convert to grayscale, convert to numpy array, resize the mask to same size as the input image. Okay, so we are resizing both the images to the same size. Then we normalize the mask also, and then we add channel dimensions. Once done, then we add the image to our images folder, and then the masks list, and then we return those two errors. And then we load both the directories, the x and y, and this is the load directory with the image size that we mention here. So we call this load function where we mention this directory path, and now we create so this is how we are creating the images and mask list. So we create the list, now we show them. Okay, Okay. Okay. So the data loading is updated to this. I say, can you give me full code with steps and explanation with updated information I had passed. I don't want to go up and down. We have already done that. We have explored, understood this all, but we are yet to write this thing. And then we build the UN model, and this is also going to be a little lengthy. Then we compile the model. This is very basic that we have been doing it. And then we train the model on the training data, and then evaluate the model and visualize the result. So let's do this. Let's stop this for now and split it into the part 2 video. So that I'll upload today only. But I am going to take some time off, like 15 minutes to relax, and then come back with a fresh mind and then start solving it. So thank you very much. Let's meet in the part 2 of this video.